Welcome to Lecture 10, in which we will discuss entanglement and the measurement of one qubit of a two-qubit state. And you will recall that actually I had hoped to discuss all of this in Lecture 9, but underestimated the amount of time that lecture would require. And so now we're basically continuing Lecture 9 in this lecture now, which is, of course, is Lecture 10. I'll just start off with an example here. Let's suppose that we have the state C, which is given by the following expression: square root of 15 over 42, 0, 0, plus square root of 20 over 42, 0, 1, plus square root of 3 over 42, 1, 0, plus square root of 4 over 42, 1, 1. And the first question we want to consider is the following. If we measure the first qubit of this state with the standard basis, what are the probabilities for the various outcomes? Now again, I want to stress we're measuring only the first qubit of this two-qubit state. Well, I would suspect that although we have never seen a problem like this before, if I just pose this question to you, you might proceed in the following way. First of all, if you were the skeptical type of a person, you might want to guarantee that this truly is a state here. But it really is. If you will notice, each one of these kets is orthogonal to each of the other kets. And when we take then the inner product of this with itself, we just come up with this squared plus this squared plus this squared plus this squared. And so we would get 15 over 42 plus 20 over 42, which makes 35 over 42, plus 3 over 42 is 38 over 42, and then 4 over 42 gives us 1. So indeed, this has a magnitude of 1, and this is an acceptable state. And so now, having checked that and verified that this is correct, then if, first of all, since we're measuring that first qubit in the standard basis, which consists of 0 and 1, we know that those are the two possible outcomes for the first qubit, 0 and 1. And so I think that you might very well guess, that the probability that the first qubit is 0 is square root of 15 over 42 squared plus the square root of 20 over 42 squared. which would be 35 over 42. And if you guessed that, you would actually be correct. And likewise, you might guess, left out the word guess, you might guess that the probability that the first qubit is 1 is square root of 3 over 42 squared plus the square root of 4 over 42 squared, which would be 3 over 42 plus 4 over 42, or 7 over 42. And that is also correct. But I want to now spend the next few minutes working on this, and I will follow the procedure that is discussed in examples 3.3.3 and 3.3.4 in your book. And I think that this will help to convince you that indeed these probabilities are correct. And it will also tell us one other thing, which is the following. Let's suppose, in fact, I want to go ahead and put this question down. So let's suppose you measure the first qubit to be 0. What is the resulting state? Now, if we measure the first qubit to be 0, you might reason as follows. That means that we have not measured this part of the state. We have obtained this part of the state. So you might guess that the resulting state is the square root of 15 over 42, 0, 0, plus the square root of 20 over 42, 0, 1. And this is not too far off, but this is not a state. This is not a state. Because it does not have magnitude 1. So in other words, we need, for those of you who've heard this kind of terminology before, we need to normalize that state. And so this is where we get now to the procedure that your book outlines in examples 3.3.3 and 3.3.4. And let me just go through this procedure with you because it's really quite simple. And once you see it, then I believe that it will all make perfectly good sense. And this will all come together in a really nice way. So let's observe the following. Okay, first of all, we're going to write down C once again is the square root of 15 over 42, 0, 0, plus the square root of 20 over 42, 0, 1, plus the square root of 3 over 42, 1, 0, plus the square root of 4 over 42, 1, 1. Now, since we're measuring just the first qubit of this state, I want to separate out the first qubit in the following way. This will be equal to, for the first two terms, the first qubit is 0. So I'll have 0 times the square root of 15 over 42, 0, plus the square root of 20 over 42, 1. And then in the second two terms, the first qubit is 1. So we'll have plus 1 times square root of 3 over 42, 0, plus square root of 4 over 42, 1. Now, this is all set up so that now you can see if we measured 0 for the first qubit, then the resulting state should be somehow related to this, but with some kind of a normalization factor. And likewise, if we measured the first qubit to be 1, then the resulting state should be this, but again, with some kind of a normalization factor built in. And so the way that we get this normalization factor is the following. For the first term, what we will do is take the square root of this coefficient squared plus this coefficient squared. So we'll have the square root of the square root of 15 over 42 squared plus the square root of 20 over 42 squared. And for the second term, we'll take the square root of the square root of 3 over 42 squared plus the square root of 4 over 42 squared. Now, this first term, of course, becomes, when we do the arithmetic, squaring the first term, of course, gives us 15 over 42. Squaring the second term gives us 20 over 42. So we have square root of 35 over 42. And similarly, for the second one, we get the square root of 7 over 42. Now, we don't want to change the identity of C. So if we divide by this term, if we divide this first term by this, then we must also multiply it by that. And similarly, if we divide this second term by this quantity, we must also multiply by that quantity. And so what we would get is the following. First, I'll multiply the first term by the square root of 35 over 42. So square root of 35 over 42 times 0. Now, since I have multiplied the first term by the square root of 35 over 42, now I must divide it by the square root of 35 over 42. And I'm going to do the division inside so that, and the whole point here is that what's left inside will have a magnitude of 1, and so it will represent a state. So if I divide both of these terms by the square root of 35 over 42, you can see that I'll get square root of 15 over 35, 0, plus square root of 20 over 35, 1. Now we'll do the same kind of procedure with the second term, and if you're feeling brave, I would encourage you to stop the video for a moment and try to do this for yourselves and then come back. Okay, so in this case now, we want to normalize this so that it has a magnitude of 1. And we've already seen that its magnitude right now is the square root of 7 over 42, so we're going to divide by that number, but then we must multiply by that number. So we get square root of 7 over 42 times 1, and then open parentheses, square root of 3/7 0 plus square root of 4/7 1. And now we have a situation where this, and we can easily see it too. Notice that this is now a state. Because this ket has a magnitude of 1. If we square this, we'd get 15 over 35 plus 20 over 35 is 35 over 35. So this has a magnitude of 1. Likewise for this, we square the first term, we get 3/7. Square this, 4/7, and 3/7 and 4/7 is 1. And so, and furthermore, this squared, this number squared right here, which of course would be 35 over 42, that will give us the probability of measuring 0 for the first qubit. And this one squared, 7 over 42, would give us the probability of measuring 1 for the first qubit. And notice that that's exactly the probabilities that we had before. But there's now another very interesting piece of information that we can get out of this if we'll pay just a little more attention. And so let's proceed as follows. Notice, of course, that this first term could be simplified. We have square root of 5/6 times 0. And then inside, if we simplify that, we will get square root of 3/7 0 plus square root of 4/7 1 plus square root of 1/6 1 times square root of 3/7 0 plus square root of 4/7 1. And lo and behold, if you look at that closely, you see that the parenthetical terms for both of these are exactly the same. And so this means that this can be factored in the following way. We have square root of 5/6 0 plus square root of 1/6 1. And then if you wish to put in the x just to emphasize, square root of 3/7 0 plus square root of 4/7 1. What do we conclude from the fact that psi can be written in this way? Well, the fact that psi can be written in this way shows that psi is unentangled. Furthermore, the probability that the first qubit, let's see, probability that the measurement of the first qubit yields 0 is equal to 5/6, and the probability that the measurement of the first qubit yields 1 is 1/6. But now, and this is the critical point, it is very important to note that the measurement of the first qubit does not in any way affect the measurement of the second qubit. In this case. And let me emphasize what I mean. This parenthetical term is the second qubit, and it's exactly the same whether the first qubit is 0 or the first qubit is 1. So if we measure 0 for the first qubit, then we would conclude that the resulting state would be 0, the 0 ket times this. And on the other hand, if we measure 1 for the first qubit, we would conclude that the resulting state is the ket 1 times this. So in either case, we conclude that the identity of the second qubit is this. And what that means is that after measuring the first qubit in the standard basis, if then a measurement was performed on the second qubit in the standard basis, then the probability of getting a 0 for that second qubit would be 3/7, and the probability of getting a 1 for the second qubit would be 4/7, regardless of what you had measured for the first qubit. And that's true because this state is unentangled. But we're going to see that, and this is one thing that's very important about quantum computing, is that, or something that plays a very big role in it, is that when we have an entangled state, the measurement of the first qubit affects the measurement of the second qubit. They're not, you cannot measure them in an independent way. And so this is something that's non-intuitive, but it is the way it works, and it plays a big role in quantum computing. So that's our first example of the measurement of of 1 qubit of a 2-qubit state. Now consider the same state but this time we will measure the first qubit in the Hadamard basis. Okay, so how would we do this? Well, again, let's start by writing down the expression for C. We have square root of 15 over 42, 0, 0, plus square root of 20 over 42, 0, 1, plus square root of 3 over 42, 1, 0, plus square root of 4 over 42, 1, 1. And again, since we're going to measure the first qubit, let's go ahead and separate that out. So we will get 0, we'll get square root of 15 over 42, 0, plus square root of 20 over 42, 1. and here square root of 3 over 42, 0 plus square root of 4 over 42, 1. Now, since we are measuring the first qubit and the Hadamard basis, let's go ahead and express 0, this 0 here, and this 1 in terms of the Hadamard basis. So we have 1 over square root of 2 plus 1 over square root of 2 minus and square root of 15 over 42. Now we keep the second qubit of the state in the standard basis. There's no need to change it because right now we're just talking about measurement of the first qubit. Plus square root of 20 over 42, 1. And then, just as we changed 0, converted it to the Hadamard basis, so will we now convert 1, express it in terms of the Hadamard basis. So we will get 1 over square root of 2 plus minus 1 over square root of 2 minus, and then square root of 3 over 42, 0 plus square root of 4 over 42, 1. Now, we have a little bit of algebra to do here, and I don't want to take up too much time with this. Let's see. I guess I'll go ahead and say the following. Let's see. Well, I believe I can do this. I believe I can do this. We will get square root of 15 plus the square root of 3 over the square root of 84 times plus 0 plus the square root of 20 plus the square root of 4 over the square root of 84 times plus 1 plus square root of 15 minus the square root of 3 over the square root of 84 times minus 0 plus the square root of 20 minus the square root of 4 over the square root of 84 times minus 1. And I haven't skipped much there at all, just a little bit to expedite this just a little. And now let's split out the plus and the minus, so we get plus times the square root of 15 plus the square root of 3 over the square root of 84, 0 plus square root of 20 plus the square root of 4 over the square root of 84, 1 plus minus times the square root of 15 minus square root of 3 over the square root of 84, 0 plus square root of 20 minus square root of 4 over square root of 84, 1. Now, before we proceed any further, I hope that you will take a moment to consider a question. When we measured the first qubit of this state with the standard basis, you will remember that we concluded that basically the term in parentheses here, which represented the second qubit, it was the same in both cases, which meant that regardless of what our measurement for the first qubit yielded, that would not affect our measurement of the second qubit of the pair. And that was true when we measured the first qubit in the standard basis. But now we're measuring the first qubit in the Hadamard basis, and certainly just to glance at this expression and this expression, they look fairly different. So the question is, ultimately, are we going to have the same conclusion as before, that the measurement of the first qubit does not affect the measurement of the second qubit, or will it be different now that we're measuring the first qubit in the Hadamard basis? Well, I'll leave you in suspense for a moment. I hope you will really think about that, and then make a decision. But for now, let's see how this would proceed. So I'm not brave enough to keep on doing all the algebra with the square roots. I'm just going to go to the calculator and get some numbers. And so if you do simplify these expressions with your calculator, I believe that you will get the following. The first term becomes plus times 0.6116 times the 0 ket plus 0.7062 times the 1 ket. And then for the second parenthetical term, we will have 0.23360 plus 0.26971. Okay, now this is just as we were doing things before, and remember that what we want in each parentheses, and by the way, again, these parentheses, these terms don't look the same right now, but we want inside each parentheses to have a state. In other words, it must have a magnitude of 1, and neither one of these has a magnitude of 1 at the moment. So what we need to do is, for this first term, we'll need to multiply and divide by 0.6116 squared plus 0.7062 squared, square root. And for this term, we will multiply and divide by the square root of 0.2336 squared plus 0.2697 squared. And when you do that, you will find the following. Now remember, again, what we're going to do is we're going to take whatever this is equal to, See, we need to divide by that to make this normalized in here, but if we're going to divide by it, then we must multiply by it out front so we don't change the overall expression. And similarly here, we need to divide by this expression to normalize what's in here, but once we've divided by it here, we need to multiply it by out front. And so when you do those mathematical manipulations, you will get the following: 0.9342 times plus 0.6547 plus 0.7559 plus, maybe I'll just continue it on the next line, plus 0.3568 minus times 0.6547 plus 0.7559. And we notice, sure enough, that just as before, the parenthetical expression representing this second qubit is exactly the same for both cases, which means that this C, let's go ahead and make the observation, we could write this as 0.9342 plus 0.3568 minus, and then if we wish we can put our X in there, 0.6547 plus 0.7559. And so again, and this should not surprise us, because remember, we said before that whether or not a state is entangled does not depend on the basis that we use. It depends on the decomposition, but it does not depend on the basis. So the fact that we use the standard basis in the first case and the Hadamard basis in the second case is completely irrelevant. So again, we conclude that this state is unentangled. And the probability that measurement of the first qubit will yield plus is equal to 0.9342 squared. The probability that the measurement of the first qubit will yield minus is equal to 0.3568 squared, and regardless of the measurement of the first qubit, the second qubit will be 0.6547 plus 0.7559 And therefore, if we measured that second qubit in the standard basis, the probability of getting 0 would be 0.6547 squared. The probability of getting 1 would be 0.7559 squared. And that statement is true regardless of what you get for the first qubit. So I hope that made good sense to you. And now we will see the very important difference when we measure the measure one of the qubits of an entangled state. So let's say now consider the measurement of the first qubit of the entangled state and the example that we will look at here will be 1/2 0 0 minus 1/2 0 1 plus 1/2 1 0 plus 1/2 1 1. Now I would advise that you go ahead, just as a nice review, stop the video for a moment and convince yourselves that this state is entangled, and then let's come back and resume. Okay, so hopefully now you have concluded that the claim is correct, that this is indeed an entangled state, but even if you did not conclude that or had some trouble in concluding it, it will become obvious as we work through this example. So we're going to consider the measurement of the first qubit of the entangled state, and we'll say using the standard basis, because that'll make this nice and easy. So again, just as in our previous cases, since we're going to measure the first qubit, we will separate it out. So we get 0 times 1/2 0 minus 1/2 1 plus 1 times 1/2 0 plus 1/2 1. And now, if we proceed in the normal way, we will want to divide and multiply this term by the square root of 1/2 squared plus 1/2 squared, and we will divide and multiply this term by the square root of 1/2 squared, plus 1/2 squared. And for this first term, just to make it perfectly clear, of course it turns out to be the same, but I'll say plus minus 1/2 squared. Okay? And of course in each case that becomes square root of 1/4 plus 1/4, which is 1/2, square root of 1/2. So C is equal to square root of 1/2 0, and then 1/2 divided by the square root of 1/2 is the square root of 1/2. 0 minus square root of 1/2 1, and then the second term will become square root of 1/2 1 times the square root of 1/2 0 plus square root of 1/2 1. And really, this is fine to write this in this way. Yeah, well, we might as well just leave it this way. But notice what we have here. Okay, the probability that measurement of the first qubit will give us 0 is this term squared. So it's 1/2. And the probability that the measurement of the first qubit will give us 1 is this squared. So that's also 1/2. So the probability of the measurement of the first qubit will give us either 0 or 1 is the same. It's 1/2 either way. But notice that this parenthetical term following 0 is not the same as the parenthetical term following the 1. So this means this state is entangled. And furthermore, if we measure the first qubit as 0, the second qubit must be square root of 1/2 0 minus the square root of 1/2 1. But if we measure the first qubit as 1, the second qubit must be square root of 1/2 0 plus the square root of 1/2 1. So in other words, the measurement of the first qubit affects the measurement of the second qubit. And this is truly a fascinating idea because, well, for instance, if you look in your book at section 3.4 at the Eckert protocol, it depends explicitly on this feature of entanglement. And for instance, the idea there is that you send an entangled state to Alice and Bob, and if well, maybe I should show the details of this. So let's talk about Eckert protocol. And I won't go into a great deal of detail about this because we don't yet have all the knowledge that we would need to thoroughly discuss the detection of any interception of this protocol. This protocol, like the BB84 protocol and the B92 protocol, this protocol will allow us to detect if Eve has been intercepting. But we're not quite ready to understand how that works yet. That will be a little bit later. But just to give you a brief outline of it, suppose we send the entangled state 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1, to Alice and Bob. But let me be a little more specific. Alice will receive the first qubit and Bob will receive the second. And here we just want to note that Alice and Bob may be separated by a large distance. Now, before I go any further, I want to encourage you to verify for yourselves that this state is entangled. Furthermore, you might also note that that state if it were written if both qubits were written in terms of the Hadamard basis, this state is equivalent to this. Now, having written these states in this way, we can see immediately that, again, now remember, Alice has the first qubit, and Bob, who might be very far away, receives the second one. And Alice and Bob will randomly decide whether to measure their qubits with the standard basis or with the Hadamard basis. Okay, so let's think about Alice for a moment. When Alice measures the first qubit with the standard basis, she has a 50% chance of measuring 0 and a 50% chance of measuring 1. If Alice measures the first qubit with the Hadamard basis, she has a 50% chance of getting plus and a 50% chance of getting minus. However, and this is the key part, if Alice measures that first qubit, let's say that she measures it as 0, then that means that the qubit, okay, let me back up. If Alice, just want to be specific, if Alice uses the standard basis to measure the first qubit, and if she measures a 0, that means that Bob's qubit is 0. And so if he measures it with a standard basis, he will certainly, with a probability of 1, he will measure it as 0. Likewise, if Alice measures the first qubit in the standard basis to be 1, and if Bob, then that means that Bob's qubit will be 1. Now, if Bob happens to use a Hadamard basis and his qubit is 1, then he has a 50% chance of measuring minus and a 50% chance of measuring plus. But if he measures that second qubit with the standard basis, then he will, with a probability of 1, measure 1. So to summarize all that, if Alice and Bob use the same basis to measure their qubits, they will certainly get the same number. But if they use different bases, then there's only a 50% chance that their numbers will be the same. And therefore, with the Engr protocol, what would happen is, in establishing a quantum key, we would have some third party send this entangled state to Alice and Bob, and Alice and Bob randomly now will use either the Hadamard basis or the standard basis to measure these. And Alice measuring the first qubit, Bob measuring the second qubit. And then after they've done the measurement, they can discuss publicly what measurement bases they used for each case. And they will know when they use the same measurement basis, they will know for sure that they arrived at the same number, the same bit. And on those cases where they used a different measurement basis, they will discard those cases, similar to what is done in the BB84 protocol. But the thing that makes this work is the fact that this state is entangled. If it were unentangled, Alice would not be able to conclude from her measurement of the first qubit what Bob would measure for the second qubit. Even if he used the same measurement basis, she would not be able to say. For instance, just to emphasize this point, let's go back up here to the first example we looked at. See, if the person sending Bob and Alice were sending this state, well, as we can see from this analysis here, if Alice is measuring the first qubit, 5/6 of the time she should measure 0, and 1/6 of the time she will measure 1. But regardless of whether she measures a 0 or a 1, Bob, who's measuring the second qubit, will measure 0 3/7 of the time and 1 4/7 of the time. And what Alice does has no effect on what Bob sees. But in the case of an entangled state, if Alice and Bob both use the same measuring basis, and let's say in this case, just for the sake of simplicity, they use the standard basis, and Alice measures a 0, then this is where we are. If Alice measures a 0, then that means that the second qubit is definitely 0, and so if Bob is using the standard basis as well, he will measure a 0. So this is the idea. This discussion of the measurement of one qubit of a 2-qubit state, we see now how it proceeds, and we can also see why the idea of entanglement is so intriguing. And it's certainly counterintuitive that the measurement of one qubit would affect the measurement of the other one, but this is in fact the case. And it's one of the features of quantum mechanics that helps to make quantum computing possible. So I hope that that's been clear, and now let's look at some problems. Okay, so the problems for this lecture are as follows. We suppose that we send the first qubit of the state square root of 2 over 25, 0, 0, plus square root of 3 over 25, 0, 1, plus square root of 8 over 25, 1, 0, plus square root of 12 over 25, 1, 1. This state will be sent to Alice and Bob, but we're going to send the first qubit to Alice and the second qubit to Bob. And we suppose that Alice and Bob both use the standard basis to measure their qubits. Now, having said that, we have 4 questions. If Alice measures the first qubit as 0, what is the probability that Bob will measure the second qubit as 0? The second question, if Alice measures the first qubit as 0, what is the probability that Bob will measure the second qubit as 1? If Alice measures the first qubit as 1, what is the probability that Bob will measure the second qubit as 0? And finally, if Alice measures the first qubit as 1, what is the probability that Bob will measure the second qubit as 1? And in each one of these 4 problems, A is 1/5, B is 4/5, C is 2/5, and D is 3/5. So those are the 4 questions, the 4 in-lecture questions for Lecture 10. And then I'll go ahead and give you a hint as to what I'm going to do in class. In class, I'm going to give you exactly the same kind of problem, but with a different state. And once again, I will ask you about probabilities like this. So I don't know about you, but I think that this is really interesting. I hope that you're enjoying it as well. And I hope that you'll give these problems a good shot. So good luck, and that ends Lecture 10. As I say, good luck.